So here's part 4 again, and here's a brief reminder about how we calculate a rate of change, a gradient, based upon something like this. Now, in part 4, we had a bunch of gradients. We have this one, this one, this one, this one, and this one. So I can only calculate the gradient for bits and pieces, and I'm going to focus on calculating the gradient here. So just a reminder then that we've got, this is our formula for the gradient of a straight line. It is only for a straight line. So we have y2 minus y1 over x2 minus x1. You should be very familiar with that now. This might be a bit new, but it's important that you understand what this means. This is delta, capital delta. And in mathematics, it is used for discriminant, if you remember from our previous unit, but it also means to describe the change in the value. So this is saying change in y divided by the change in x, which is really what y2 minus y1 is. It's looking at this change here, and x2 minus x1 is looking at this horizontal change here. So in our problem, we had 4.5, 8 as being a coordinate of after the football field. So that means 4.5 hours, 8 kilometers away from home, and then 6.5 hours at 0 kilometers from home. I had traveled back home in 2 hours. Okay, that's from part 4. So how will we calculate that? Well, as we said, it's a change in y. So I simply write down the y coordinates. Doesn't matter which order, but I'm just going to go top to bottom. So it's going to be 8 minus 0. That's the change in y. And then we've got change in x, which is 6.5. Oops, sorry, I beg your pardon. Got to be in the same order. So 4.5 minus 6.5. So at the top, we've got 8 minus 0, which is 8. On the bottom, we've got 4.5 minus 6.5, which is 2, negative 2 to be precise. And that gives us 8 divided by negative 2, which is negative 4. And I'll put the units in for context. It's negative 4 kilometers per hour. Now, what does that mean? It means that I traveled at 4 kilometers per hour. That's my speed. And the negative in front of it means I was traveling in the context of this problem, I was traveling towards home as opposed to away from home. So away from home was a positive gradient, towards home was a negative gradient. So I was traveling towards home at a speed of 4 kilometers per hour. Okay, you should already be familiar with that. So that's just a very brief check on it. But I want to go one step further. Here it is represented in Desmos, same graph. Travel here, travel here, travel here, travel here, travel here. And again, I'm going to focus on just the journey home. In reality, I wouldn't have got here and said, right, I'm starting off, and then I would have gone 4 kilometers per hour, bang, 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 all the way through. It's unlikely. Chances are, when I started off after my trip, I would have been a lot fresher. After my football match, watching it, I would have been a lot fresher, so I probably would have traveled a little bit faster. And so that would have been a much steeper graph. So it would have been like this. For travel home, doesn't take long, so it'd be a rather steep graph. And then as I got towards home, I might be a little bit more tired, so it might be less than 4 kilometers per hour. So in other words, for a small period of time, it might be quite a long change in x. So this is just a representation of what the travel time would have been on average. It actually might have looked something like this. Steeper to start with, and as I got further closer to home, I start to slow down in my speed because I'm getting a bit more tired. So this blue line then represents an average rate of change or an average gradient, whereas in actual fact, I may never have traveled at 4 kilometers per hour, or if I did, it might be just one of the spots along here. And for the rest of it, I was either traveling faster or slower. So the average basically just says, well, if I just sort of look at how long it took me to take and how much distance I had to travel, on average, I would have gone. If I'd sort of broken all this down into equal pieces and shared the same speed for each piece of the journey, it would be 4 kilometers per hour each part, even though the journey itself didn't really take 4 kilometers per hour at any particular point, or maybe only a few points, something like that. So we have this concept then that we can estimate, I suppose, a journey where the gradient changes frequently. We can calculate an average by considering the straight line between the start and the end point. And that's what we call the average rate of change, and that's what you're going to calculate today. If you have a look at, say, for example, part 2, and again, your calculations and graph will look different from mine because I use slightly different values. You were asked a bit further down to work out the average rate over the first 50 seconds, and you can see here I've got 3.9 over 50. How did I work that out? Well, I looked at the coordinates at 50 seconds and saw that the y coordinate was 3.9 litres. So really all I'm doing is I'm taking this graph and I'm saying if I produce a straight line from 0 to 50, which is 3.9 on my graph, what would the gradient of that straight line be? 3.9 over 50. Similarly, for 25 to 50 seconds, you can see I've got effectively a coordinate here, 50, 3.9, that's those two, and 25, 2.45. So I subtracted the two y coordinates from each other. That's a change in y, change in litres, change in volume, divided by the change in time, 50 minus 25. And that gave me a litres per second over that. Not that the flow rate would have been actually that value at any particular point over the 25 to 50 second time frame, but on average, the flow rate happened in that way. So I've effectively made the bendy line straighter by working out an average, and it only makes sense over that time period. It doesn't make sense if I then look at 26 seconds or 32 seconds or 49 seconds. The change, the flow rate is actually going to be different from my average value, but it does give me a sense of what's happening over that time period. So that is basically in terms of working out the average. That's what you do. So a really brief summary here, and a little bit more notation, just a little bit more. It's an important one though. So generally speaking, if I have a set of axes here, x, and on the y-axis is f of x for some function f of x, doesn't matter what it is. I'm going to have an x coordinate of a here. So I've substituted in a specific value for a here. A could be 1, 2, 7, 9, whatever. And then I've got another value here, x value here, which is b. Okay. Then if I work out the straight line between these two, work out the gradient of the straight line between these two, this would be the average gradient for this part of the blue line. Okay, so this red line is the average gradient or average rate of change for the blue line. Now you notice I've only got the x coordinates here. I really need to put the y coordinates in, but just like I'm not using x2 and x1, I'm not going to use y2 and y1 either. What does it kind of look like though? So x, at x equals a, what does y equal? Well, to get the y value, I would have to substitute a in for x in the function, right? So in other words, I have to look at the function at point a, so y equals f of a. So this is really f of a in here. And similarly for b, this is really important, this point, the value of y would be found by substituting the value b into the function. So that would be f of b. And so I can put f of b here. And that becomes my two coordinates, a and f of a, so that's x1, y1, b and f of b, that's like x2 and y2. Okay, so we can talk about the gradient, the average rate of change then, as being the change in y. Now this would be f of b, that's like y2, minus f of a. Okay, so that's the change in y. And it would be over b, the first x coordinate, minus a, the other x coordinate. So that would be like a change in x. And that's how we work out the average rate. Okay, so if you look at your textbook, you'll see this summary here with a bit of language as well. So the secant, just so you know, the secant line is the actual line itself that goes on forever in both directions. It's this blue line here that goes on forever. It's the line which passes through 2 points on a curve. Okay, so there's a point here and a point here, and the secant line or the secant passes through those 2 points. If we just zoom down into the bit of the line, otherwise known as a line segment, between those 2 points, that's called a chord. So this bit here is the chord, the secant or secant line is the entire line. And because it's a line, we could express it as a function, like a linear function. So y equals mx plus c for some values of m and c. Okay, so there you go. And it says here, for a function, the average rate of change with respect to x over the interval a, b, that means from a including a to b including b, is the gradient of the secant line. In other words, we can use our gradient formula through, these are coordinates now, not intervals, through a, comma, f of a, I just talked about that a second ago, and b, comma, f of b. So x1, y1, x2, y2. So we have y2 minus y1, f of b minus f of a, over x2 minus x1, average rate of change. Okay, so these are basically rate of change problems that I've asked you to do. So what you're going to do for the next bit is you are going to do exercise 16C, and you've got a few questions to do. Questions 3, 4, 6, and 7. And from question 3, you can just do C and D. So it says find the average rate of change. So you've got 2 points here, and you are just using your gradient formula in order to work out what that gradient would be. And then there's some interpretation questions here in 4, 6, and 7. So all the very best with it. Please feel free to ask questions if you're not too sure what to do. Good luck.